But in order to use that integrated rate law equation, we need the decay constant. We do not have the decay constant. We have the initial mass of the sample, we have the half-life, and we have time. In order to get the decay constant, we can use the half-life and the half-life equation, rearrange it, and solve for the decay constant, which will be the natural log of 2, or the 0.693 divided by 66 hours. Because our half-life is in hours, that'll give us a decay constant in units of 1 over hours. Now we can use this form of the integrated rate law and plug in our initial mass and solve for our final mass. However, we just determined a k value with units of 1 over hours, and we have a t value with units of seconds. So we need to reconcile that by making certain that the units of time and the units for the decay constant are the same. So I will convert my 1 over hours into 1 over seconds. Then I can simply plug in my values, having the number of radioactive nuclides, or the mass of radioactive nuclides, at time t being equal to x, and then solve for x, giving me 3.107 times 10 to the negative 2 milligrams, or 31.1 micrograms. Now what if I were asked to solve for the initial rate, or the number of decay events occurring at time 0, and the number of decay events occurring after 1.19 times 10 to the 6 seconds had passed? Well, if you remember, rate is simply equal to k times n. So the initial rate would be equal to k, which is 2.92 times 10 to the negative 6, 1 over seconds, times n. Well, n is given to me in milligrams. So if I want to report the rate in decay events, or radioactive nuclides decaying per second, then I need to convert my 1 milligram into number of radioactive nuclides. And I can do this very easily by simply starting with the milligrams of the radioactive molybdenum that I have, dividing by 1,000 milligrams for every 1 gram, and then converting the grams into moles. Now I do not have the molar mass of molybdenum. I could use the average molar mass, but it does tell me that the radioactive nuclide that I have is molybdenum 99. So to get an approximate value, I'm simply going to use a mass of 99 grams per 1 mole. And then I'll convert the moles to number of radioactive nuclides. This then will give me the number of radioactive nuclides that I have as the reaction starts. The rate then will be equal to the decay constant multiplied by the number of radioactive nuclides, which, when I multiply by 2.92 times 10 to the negative 6, gives me 1.78 times 10 to the 13. So this is telling me that I have 1.78 times 10 to the 13 radioactive decays occurring every second at the initial mass of 1 milligram. If I did not change this mass to nuclides, and I were to just multiply this by 1, then essentially my units would be milligrams decaying per second. More often than not, we express the rate as nuclides decaying per second. So typically the n value here is in number of radioactive nuclides, where the n value for the integrated rate law could be moles or grams or radioactive nuclides. I would then do the same thing to determine the rate after 1.19 times 10 to the 6 seconds. I would take this mass and convert it to number of radioactive nuclides, and then multiply it by the decay constant. and you will notice that the rate will be less after time has passed.